The extremely high altitudes at which modern aircraft can operate effectively and the ever-increasing speeds obtainable at all altitudes introduce certain new problems in aerial tactics. This should be of interest even to experienced fighter pilots. In this film, we will show the tactics developed for high-speed, high-altitude aircraft as solutions to the following three problems: intercept, escort and attack, and defense problems. First, let's see what's involved in the intercept problem. We'll assume that one of our carriers is the enemy target. A bomber at 40,000 feet needs only to get within 6 miles of its target to dump its bomb load. If the bomber is traveling 7 miles a minute, the intercept must be made another 70 miles away to allow 10 minutes for combat, a fairly well-established figure. Another 14 miles or 2 minutes must be allowed for the alert and time to scramble. If the fighter can climb to 40,000 feet in 20 minutes, another 140 miles is required, and the bomber must be detected 230 miles away. If the fighter requires 35 minutes to get to 40,000 feet, the bomber will travel 245 miles and must be detected a total of 335 miles from the carrier. The importance of advance warning, either by a picket destroyer or AEW, is apparent when we see the distances covered. Because we cannot pick up all targets at a sufficient distance to intercept them, there will undoubtedly be situations in which an airborne combat air patrol will be necessary. The chief problem in this case is the time required to relieve CAP on station and the fuel used while the aircraft are awaiting a vector. The logistics of maintaining a constant airborne CAP is an important consideration and makes the use of this technique difficult. Up to this point in the intercept, the pilot is working under the direction of the air controller in CIC. In air control work, knowing the pilots and the characteristics of the aircraft being used are very important to the air controller. At very high altitude, the pilot is normally operating close to the performance limitations of the aircraft. The controller must be familiar with these limitations, because if he asks for speed or maneuvers in excess, the pilot either cannot comply or may stall or encounter compressibility. For example, if the controller calls for a tight turn and expects a turn of about a mile radius, when the best the pilot can do is a turn of 1.5 miles radius, it is apparent that the pilot will not end up where the controller wants him. Also, the air will be cluttered with conversation if many pilots and the controller are talking back and forth, even following good radio procedure. And because talking at high altitude is difficult and hard for the controller to understand, every effort should be made by the controller to reduce the necessary talk by the pilot. Abbreviated voice procedures are used as much as practicable to reduce the amount of voice radio traffic. Using all the skills of a good controller, the fighters have now reached the point of tally-ho. Generally speaking, visibility in jet fighters is better than in reciprocating engine fighters. However, it is easier to detect aircraft above you than below. How quickly you make a visual detection depends upon such things as clouds, the position of the sun, and whether or not the target is leaving contrails. Incidentally, conversely, as we see here, if you fly in the contrail level, you advertise your position even though your aircraft may not be seen at all. If the height-finding radar used by the air controller is accurate enough, it's possible to bring the fighters in at the correct altitude to put the target approximately 1,000 feet above the fighters. This is the most desirable position for visual detection. Selecting the most advantageous intercept approach angle is part of the intercept problem. Here is the ideal position for a tally-ho and the resulting attack run after climbing into position level with the target. Against high-altitude, high-speed targets, only very mild runs can be effective with the lead pursuit type of fire control system. Any appreciable amount of deflection produces pursuit curves that cannot be flown without entering the buffet range. This limitation seriously affects the planning and execution of such attacks, and forces the pilot to make low deflection runs. In a head-on attack, the closing speed may be from 1,000 to 1,200 knots. Should you fail to get a hit on a head-on intercept, or should you miss the visual intercept and have to turn back, an extended tail chase will result. If the other aircraft is also a high-speed aircraft, it may be impossible to overtake it before it reaches the release point. For this reason, a head-on intercept is only used when time will not permit the controller to bring the fighters into a beam position, or when the number of fighters in the line is such that one of them is almost bound to make a kill. If the action occurs at medium or low altitudes, and the fighter has effective speed brakes and a suitable speed advantage over the target, high side or direct overhead attacks can be made. This type of attack allows the bomber's gunners little chance to fire. Rather than the entire division attacking from one side, one section may come in from one side while the other section makes a coordinated run from the other side. Another useful type of attack is made from above and behind in a line abreast formation. Because of the high speeds involved, very smooth, low G runs must be made. This attack may be forced by high altitude, high-speed targets against which high deflection runs cannot be effected. The breakaway is made to the beam and below. In all aerial tactics, whether offensive or defensive, never let the fight degenerate into individual melees. Always join up the division, or at least the sections, gain altitude or position advantage, and make another attack. And remember, in intercept work, breaking up the entire enemy formation is more important than individual kills. Now let's consider the second problem in aerial tactics, that of escort and attack. We'll start with the escort half of the problem. Of course, the maximum combat radius of the high-speed escort aircraft will determine a range beyond which fighter escort cannot be supplied. However, the economical cruising speed of the jet fighters is so much faster than the speed of the conventional attack aircraft that they cannot cruise or remain in company throughout the trip to a distant target. Unless operations are carefully timed, the escort may not be on hand when needed. To avoid this, the strike group is first launched and proceeds into the target. At a predetermined time later, the escorting fighters are launched, and because of their superior speed, overtake the strike group at a point of rendezvous en route. The escort clears out any enemy air opposition as it appears. Then the fighters may, if they have no significant air opposition, make a preliminary dive bombing, rocket, or strafing attack to hold down anti-aircraft fire. They climb back up again and fly cover while the strike group makes its attack. All planes proceed back to the rendezvous together. Then the jets return to the carrier at cruising speed, which is enough faster than the attack group to put them aboard the carrier well before the attack group returns. When close escort must be used for the entire distance, a zone type of coverage is furnished. A strong sweep is first made of the corridor to the target. The strike group starts out under the cover of the task group CAP and is covered into Zone 1. The returning sweep gives cover as the strike passes through Zone 2. Another escort group, launched after the strike group, covers the strike through Zone 3 and into Zone 4. When they are back to Zone 3, the escort leaves for the carrier and another escort joins up for cover in Zone 2. When the target is a reasonable distance away from the base, close escort can be furnished all the way by use of the conventional weave. The fighters can then operate at economical cruise and still stay with the attack group. Now let's look at the problems of the returning escorts in more detail. If the weather is good and the pilots know exactly where the carrier is, and a radio check indicates that they have a clear deck, the most economical practice is to begin the descent from a considerable distance out. This should be made at approximately 7/10 Mach, which in most current jets is about 65 knots below the red line. The distance at which letdown is commenced should be judged to bring the planes out over the carrier at proper altitude to enter the landing pattern. However, if there is doubt about the location of the carrier, or the weather is such that it is not picked up readily by visual means, it is best not to come down until the aircraft are right over the carrier and have the carrier definitely located. In this case, the aircraft should descend only to the altitude for maximum endurance. In most jets, this is lower than the altitude for maximum range. Fuel is saved, and it is easier for the carrier to pick up the jets on their radar scopes. Maximum endurance will be achieved by using the minimum power setting necessary to maintain best endurance speed. This speed is in the vicinity of 190 knots indicated at all altitudes with the F-9F and F-2H airplanes. As the airplane weight is reduced by the fuel used, the speed may be reduced slightly. The rest computer will show the endurance under the above conditions for various altitudes and fuel states. When the aircraft has been cleared to come down from a position near the carrier, a steep descent should be made with speed brakes in order to enter the landing pattern with minimum delay. If during the descent a foul deck should occur, the descending aircraft should regain as much altitude as possible using zoom speed, level off there, and hold maximum endurance settings. It is best not to climb up to a higher altitude, since the fuel used in climbing will offset the higher fuel consumption at the lower altitude. This completes the information on escort. Next, we will see the problems of close air support using high-speed aircraft. Behind every close air support mission, the problem of the availability of fuel to make the attack is an ever-present factor, just as it is in intercept and escort work. The amount of fuel used is affected by the distance and the altitude selected for the flight into the target. If the distance to the target is great, and it will be necessary to remain on station for any length of time, the flight in must be at high altitude in order to conserve fuel. Over short distances, a low altitude approach is generally desirable because the fuel used to climb, as well as the time used, offsets the higher rate of fuel consumption at low altitude. Low-level attacks generally are favorable in any case when radar is being used against you. Because of the amount of fuel used while on station, an alternate method of supplying close air support is to have planes on alert on catapults ready to be launched when requested. This has several advantages. For one thing, the pilot sitting in the plane on the catapult has a much better opportunity to locate the target on his chart, and briefing is therefore more thorough. Also, pilot fatigue is not as much of a factor while sitting on a catapult as it is in flying. So when a pilot does get to the target, he can do a better job. And of course, it saves the fuel which would be used cruising around on station. As an example, a carrier 200 miles from the target can launch its jets, have them on the target within 35 minutes, remain over the target making repeated attacks for about 30 minutes, and return with the required reserve. The advantages of catapult-launched jets are even more apparent when the carrier is close to the target area. For example, from 75 miles offshore, jets have been briefed, launched, and have made their first firing run within 11 minutes. On a low-level attack with the target directly ahead, the flight leader flies straight at the target in a 30 to 45-degree dive at high speed. His wingman moves outboard away from the other section. The other section comes in a beam and about 100 yards away. All aircraft then converge on the target and open fire. If a high-altitude approach is made, the final attack may be initiated from this altitude in a dive that can be carried down to about 2,500 feet. In this type of attack, the dive is made using the speed brakes and is, for the sake of accuracy of fire, continued to as low an altitude as safety will permit. As recovery is started, the speed brakes are retracted so that as much as possible of the speed built up in the dive can be used to get back up to economical cruising altitude. This completes the consideration of escort and attack problems. Now let's see the third problem, that of defensive tactics. In defensive operations, The basic element can be the four-plane division of two-plane sections or two single planes. Here we see the two sections with the wingman flying close in on the leader. Sharp lookout and vigilance astern are needed to detect and thwart any attacks that may develop. On the basis of combat experience with jets, the formation shown here with the two planes of a section abreast but widely spaced has proven more successful than the regular formation. Under high speed or high altitude conditions, the wingman, if flying in close section, must concentrate too much on keeping position to be of any help either as a lookout or in defeating an attack. To help avoid detection and to be in the best possible position for defense against attack from out of the sun, sections in line abreast should be stepped down toward the sun. For the same reason, flight in the contrail level should be avoided where possible. Another consideration regarding the sun is that when orbiting a position, the figure 8 should be flown with the long axis across the sun, and all turns should be made toward the sun. High speeds result in turns of greater radius. The radius may even be so great that keeping the enemy in sight is a problem. All 180-degree or 360-degree turns must be clearly indicated by the leader and understood by all pilots in the division. The defensive weave or simultaneous turn remain the main defensive maneuvers for aircraft at high speed and high altitude. A properly detected attack can be defeated by a well-timed defensive turn into or away from the attack. With practice, a counterattack may be possible. If the formation is separated during a melee, elements should rejoin as soon as possible. At high altitude, an aircraft must be flown closer to its maximum possible performance. This requires greater pilot skill than in aircraft at lower speeds and lower altitudes. The minimum possible turning radius is achieved at the tactical speed of the aircraft. If the turn is tightened inside this limit, speed will be lost and can only be regained by easing off the turn. If the speed loss is permitted to persist, it will lead to a stall. When you stall out, you lose altitude advantage, which may be all the enemy needs to make a kill. If you are flying at a speed close to the critical Mach number of your aircraft and want to make a turn with minimum radius, use the speed brakes to get down to tactical speed as soon as possible. Since the horizon is not a good reference at high altitudes, it is desirable to use your attitude instruments to help maintain level flight in all turns. If you start to lose altitude, your speed will build up and you may get into Mach number disturbance, usually called buffet. You may have to use the speed brakes temporarily in order to regain control. If, on the other hand, you start to gain altitude, you will lose speed advantage. Even in straight and level flight, instruments are useful in preventing inadvertent gain or loss of altitude. At high altitudes, only very shallow dives are possible with the aircraft in clean condition before speed builds up to the buffet with attendant loss of control. However, good speed brakes make steep angles and high rates of descent possible with full control. When you allow yourself to get into the buffet range, you become a sitting duck for the pilot who knows how to fly his plane at maximum performance. This concludes the discussion of defensive tactics. High speeds, whether they are on the deck, on the way up to altitude, or at extreme altitudes, present some new problems in aerial tactics. In this film, we have seen some of the techniques developed to solve intercept problems, escort and attack problems, and the problems involved in defense operations. The high speeds combined with the problems of altitude itself require that the pilot thoroughly familiarize himself with all of the new techniques in order to take maximum advantage of the ability of his aircraft to go higher and faster.
A worthy sire, McDonnell's famous Phantom, the first American jet fighter to take off from a carrier deck. With the Banshee inheriting the fine basics of the Phantom, there's a marked family resemblance between the two. But this sleek fighter has more of everything than its pioneer forebear: greater speed, greater power, greater range, and increased armament. Now, while it's getting a ground inspection, let's give it the once-over ourselves. Jet engines, buried for maximum efficiency in the thickened wing roots of the plane near its axis. Their scoops gulping enough air in every minute to empty 42 railway tank cars. For higher critical speeds, the plane has been given a lofty, thin tail. While for lowered resistances, the considerably thinner wings have a miraculous hard smoothness, as do all the plane's external surfaces. Rapid deceleration, the Banshee has also been equipped with speed brakes. Navy personnel will find that the compactness and efficient installation provisions of its powerful cannon show a realistic consideration for quick, easy loading and servicing under combat conditions. The Banshee's main fuel tanks are placed directly aft of the cockpit in the fuselage, giving easy for swift refueling and maintenance. With about twice the fuel capacity of the Phantom, they furnish the Banshee a great advantage in range over its predecessor. On extra-long missions, movable wingtip tanks may be used to give it even greater range. With everything all set, a McDonnell test pilot engineer is on hand to take the plane up, an almost daily event for these veteran war flyers who still get a thrill from the jackrabbit getaway and speed of the jet-powered Banshee. Ease of taxiing reflects the good ground handling characteristics that have been built into the Banshee, with the forward placement of the cockpit and its tricycle gear combining to give the pilot a close view of his surroundings. The bulletproof windshield also does its part in giving the pilot excellent all-around sweep of vision. Like all jet planes, the Banshee requires no extensive warm-up period before takeoff, and it's in the air within less than half a carrier deck. During its climb, the pilot retracts the electrically operated landing gear, which is then covered with flush doors, as are all the plane's external mechanisms. Powerful as the twin Westinghouse jets are, the Banshee cruises at normal speeds with a minimum of vibration and noise, the two factors which contribute heavily to pilot fatigue. But fighter planes must also be capable of the acrobatic maneuvers which are often a grim necessity in aerial combat. The Banshee pilot has them all at the tips of his fingers. First, a fast roll, which, with the aid of the power boost ailerons, the big Banshee performs with all the ease and grace of a smaller plane. But now our McDonnell test pilot has business elsewhere, so we'll say so long until a little later. And while the speedy Banshee carries on with its test flight, let's take a look at the plant producing the Banshee, at the direction and with the invaluable aid of the Navy's Bureau of Aeronautics. As modern as the aircraft it produces, the McDonnell plant has over 1 million of planes for the government, to which the company has devoted its entire energy organization. The total peacetime personnel of the company has long surpassed the employment peak of 5,200 reached during World War II. Assembled the finest aircraft manufacturing equipment in America. Operated by expert workmen, these machines, ranging in size from giant hammers to small furnaces for split metals, use the component parts for the Banshee as well as other Navy and Air Force planes. In another part of the plant, the process of assembling McDonnell aircraft is concentrated. With jigs of every shape and dimension serving as support equipment and skilled personnel combine to finalize the Banshee's hundreds of parts and join them into larger units in preparation for the final assembly of its major components. A Banshee nearing completion is now ready for an important operation, the installation of its power plant. For this is the famous J-34 axial flow gas turbojet, engineered by Westinghouse to the exacting requirements of high-speed jet fighters. So it is fitting that we sketch briefly the development and production of the J-34 by transferring our scene to the Westinghouse Electric Corporation at South Philadelphia. Here in the Aviation Gas Turbine Division, a tradition of 54 years of pioneering in engines of all types has been continued by creating within 18 months the superbly functioning J-34 requested by the Navy. Translating simplicity of design into the reality of whirling metal, a workman inserts one of the blades which will rotate between the stationary diaphragms of the compressor. Before further assembly, the compressor is subjected to a balance testing machine, the first of an elaborate system of precision checks provided for all parts of the J-34. This unerringly reveals the slightest unbalance in the completely bladed compressor spindle. The compression necessary for the operation of the engine is produced in 11 stages by these airfoil-shaped blades. The straight-through flow of air in this compressor makes possible the small frontal area so essential for compact installation in high-speed fighters. Reliable as this engine is, it will require occasional servicing that must be done rapidly under combat conditions. So Westinghouse has designed a simple method of assembly, consisting merely of sections which are bolted together. The fuel manifold unit, which regulates the crucial combustion process, likewise combines simplicity with precision in its design. The fuel nozzle sprays must be pitched at exactly the right angle and have the correct rate of flow. So Westinghouse submits each unit to still another in its system of precision controls, the fuel nozzle flow rate tester. This assures that each nozzle will spray the correct amount of fuel for proper engine operation under all conditions of flight. Here, the combustion liner, with its openings of varying sizes to admit air at proper locations for combustion and mixing, is assembled on the fuel manifold section. Here at the Production Test Center, men and machines examine and record every possible reaction of the engine for final judgment as to whether the standard Westinghouse elements of simplicity in design, quality manufacture, and precision control have been blended into a perfectly functioning unit. Finally, the test is finished, and another J-34 has proved itself in every respect. And again, it has been conclusively proved that with no oscillating or reciprocating parts, the J-34 is the most powerful engine in the world for its diameter, and one well matched to the Banshee's sleekness. Speaking of that, let's watch the Banshee in action. Driven by powerful twin jets, it makes a low-level approach at the reduced speed it will be using someday for a carrier landing. Okay, so you want to play it flat-top action. Well, we'll play too and give a wave off. That's a carrier landing officer's signal that a plane is not to land aboard. The enormous reserve power in those J-34s, plus its specialized design, give the Banshee the excellent low-speed characteristics which will enable it to cope easily with this most critical carrier requirement. And when it comes to high speed, the Banshee has plenty of that too. In the especially designed pressurized cabin, the pilot will be perfectly comfortable at the high altitudes where the Banshee achieves its maximum range. The all-important question of range is also involved in another of the Banshee's notable characteristics, its outstanding single-engine performance. So let's have our pilot complete the demonstration by cutting an engine, so that we can see how the Banshee handles on just one of its powerful jets. First, notice there is no tendency to yaw. Since the engines are placed so close together, the plane remains steady in flight. The ability to operate on one engine is an invaluable safety factor in extended over-water operations. The pilot puts the plane into a shallow dive in order to bring it home with even greater speed at sea level. As the Banshee approaches its home base, the complete reliability of her single-engine operation should be very comforting to every pilot of this Navy jet fighter. Before saying farewell, the Banshee has just one more trick to demonstrate, as proof that it realizes the value of every inch of space aboard a carrier. This practical kneeling feature enables carrier crewmen to move another plane close in under the elevated tail. Thus, more planes can be stacked aboard. Naval aviators receive the very best of equipment and training. The McDonnell Aircraft Corporation and Westinghouse are proud that the Navy considers the Banshee, which they jointly developed, of a caliber to carry on the fine traditions of a fine service.